Hi, and welcome to this video where we'll discuss about how to determine the Laplace transform of functions defined piecewise. Let's start with a quick reminder from last time. Last time we defined the Heaviside function, which is a switch. It goes from 0 to 1 at time a. It flips from 0 to 1. It's called the Heaviside function. It is denoted as h subscript a. Now, a function defined piecewise is a function where, say, up until time t1, it is given by a formula f1. Then next, it is given by a formula f2 between times t1 and t2. And lastly, it is given by a formula f3. Now, these functions can be written down in a very elegant way. You can write f, your function f, is the first function, and then you do plus second minus first times the Heaviside at time t1, and you continue like this. Third minus second times Heaviside at time t2. We'll see an example in a moment. Now, of course, I need to tell you how you can determine the Laplace transform of functions like this, where you have a function times a Heaviside. Good news, there is a formula. It looks like this. It says the Laplace of a function f evaluated at t minus a times the Heaviside at time a is equal to the Laplace of f multiplied by this exponential of minus as. Of course, there is this weird thing here that the function is evaluated at t minus a, and then you multiply by ha, but this is the formula, and we'll see in a moment how we can use it. Let's have a look at an example. Take this function f, which is 3t squared plus 1, a polynomial, up until time 5, and after it is t squared plus t plus 4. Now, the first thing to do is to write it down using Heavisides. It's the first function, we copy down, 3t squared plus 1, and then it is the second function, this, minus the first function multiplied by the Heaviside. Right, and then we can just simplify a little bit. First function and the difference here times Heaviside. Now, if we want to determine the Laplace of f, that is the Laplace of this length thing, we can split it here at this plus, because the Laplace is linear. You can split it there, and you have the Laplace of the first part plus the Laplace of the second part. The Laplace of the first part is quite easy. You can do it by yourselves. There is nothing interesting here. So we'll focus on this second part. Let's have a look at the formula again. Laplace of f evaluated at t minus a, that would be t minus 5 in our case, times Heaviside at 5. The problem is, if you look here, this is a function of t. We would like, ideally, to have it written down as a function of t minus 5. I don't want to see t over here. I want to rewrite it in a way to have t minus 5. So let's see how we can do this. Here's a trick. We'll use Taylor's theorem. So your function f at time t can be approximated, but actually this is not an approximation. You'll see why in a moment. But Taylor says that you can approximate it by this, f at 5, and then you take the derivative of f at 5 times t minus 5, and you take the second derivative of f at 5 over 2 factorial t minus 5 squared, and then you take the third derivative at 5 over 3 factorial t minus 5 cubed, and so on and so forth. Yes, but this function we have here is a quadratic function, which means that this third order derivative is just 0, and all subsequent derivatives are 0. So we can stop here. And this is not an approximation, this is exact. And the good news is that on the right hand side we have t minus 5 and t minus 5 again. Let's see how this plays out in this case. So we're focusing on this function. Let's give this function here a name. Let's call it w. W is this difference, minus 2t squared plus t plus 3. I want to apply Taylor's theorem, so let me determine the first derivative of w. Not difficult to do, so you can check for yourselves. The first derivative is minus 4t plus 1. And I want my function, the derivative of my function evaluated at 5. Okay, so plug in 5 and you'll see it is minus 19. If you put 5 over here, you get minus 19. Likewise, differentiate once more, and the second derivative you will see it is minus 4. So w prime, apologies, I have a typo here, w double prime, second derivative at 5 is minus 4. Great. And lastly, take w and plug in 5, and you will see, if you put in 5 over here, it is minus 2 times 5 squared is 50 plus 5 minus 55 plus 3, minus 45 plus 3 minus 42. So we have everything we need. We have the derivative at 5, we have the second derivative at 5, we have the value of w at 5. And if you put it all together and use this formula from Taylor's theorem now, we have Wt is minus 42, the constant, minus 19 is your derivative, times t minus 5. Sorry, let me do this. Minus 19 times t minus 5. Minus, this is actually, let me explain this bit. This is minus 4, which is your second derivative. Don't forget that we need to divide by 2 factorial, and this is minus 2. So by applying Taylor's theorem, we ended up with this equivalent expression for w. And we can now use this expression to determine the Laplace transform. We need to determine this Laplace transform. This is the w we defined before, and now we're writing w this way, and see we have t minus 5 and t minus 5 again. That's very useful, because now we can use this formula. The Laplace of f at t minus 5 times the Heaviside is given by e to the minus 5s times the Laplace transform of this function f, which means that this Heaviside becomes e to the minus 5s, and now I'm taking the Laplace transform of this, treating t minus 5, let me just highlight this, treating t minus 5 as my time variable. So for me, this is my time here. This box here is my time, t. I'm treating this as t. So minus 42 becomes minus 42 over s. Minus 19t, this is my t again. Let's call it boldface t, or green t, is minus 19, 1 over s squared. Why? Because the Laplace of my green t is 1 over s squared. You need to go back to the table, of course, and check. But as we solve more and more exercises, you'll be familiarizing with these Laplace transforms. And here we have my green t squared, which becomes 2 over s cube, and I'm copying down this minus 2. And that's it. And this is how you can determine the Laplace transform of functions defined piecewise. Thank you for watching, and see you soon.